Hi, my name is Andrey Kuehlkamp, and I'm going to present our work entitled Interpretable Deep Learning Forensic Iris Segmentation and Recognition. This is the entire team that worked on this project. However, this work is a collaboration between the Computer Vision Research Lab at the University of Notre Dame and the Duchess County Medical Examiner's Office under the sponsorship of the Department of Justice. The iris is the colored tissue that encircles and controls the pupil size, regulating the amount of light that reaches the retina. Although many people already heard about iris recognition, there's still some common misconceptions about it. First, it uses near infrared light because visible light creates difficulties when subjects have very dark irises. And second, it is not the same as retina recognition, which is a different biometric mode. Iris recognition is a mature and reliable technology that has gained worldwide adoption in the last few decades, and it has been applied from voter registration and deduplication to mobile phone unlocking. The iris is particularly useful because of its temporal stability. It allows for fast and hygienic sample collection, especially important during the COVID-19 pandemic. And interestingly, it was only in the last few years that iris recognition has been shown to be applicable to deceased subjects, which is contrary to previous beliefs. As you can see in this progression, the hardest challenge to postmortem iris recognition is the decay process, which deforms and ultimately destroys the iris tissue. The good news is that as long as the decomposition process is not too advanced, iris recognition can be used much like with live images. Our collaborators at the medical examiner's office collected over 6,000 NIR images from almost 400 different subjects. The majority of these images is in the DCMEO2 dataset, which has been made publicly available through the National Archives of Criminal Justice Data. It was not until around 2015 when someone was able to demonstrate that a set of only postmortem iris images can result in over 70% correct matching. More recent work showed that we can expect correct matches up to 5 weeks after death if the subjects are kept in mortuary or low temperatures. Since then, postmortem specific methods have been created and they are demonstrated to outperform traditional techniques used in antemortem images. Some of these techniques make use of deep learning, segmentation, and feature extraction, but they offer little or no intuition at all to forensic experts regarding their results. So the main goals of a work are to create an end-to-end deep learning based postmortem iris recognition method that is able not only to give quantitative and categorical results, such as a similarity score and a match or non-match decision, but can also offer qualitative and intuitive information to the examiners. This is extremely important to the forensic examiners because this can help them to support or challenge recognition decisions that were made by an automated system by explaining how the decision was made. More important there is currently no automated iris recognition system that is able to provide such information. So the postmortem iris images are frequently disturbed by the decay process, and many of these manifest through wrinkles or constellations of highlights that end up occluding the iris pattern. So we want our segmenter to be able to identify these regions so that they are not mixed with the iris texture. So what we do is we fine-tune mask our CNN network to perform iris segmentation, and we taught it to identify these damaged regions as different objects. In the end, we get multiple masks for the iris, the wrinkles, and the highlights, which can then be combined into a map of usable iris region. So it turns out that our segmentation method was able to outperform the current state of the art in postmortem iris segmentation. And it doesn't matter if we use coarse or fine annotations, we still can get a better intersection over union than the previous method. If we take only the best results and we plot them against the postmortem interval, we can confirm that the segmentation quality declines as the postmortem interval increases. But that is expected. What we could also see is that our method is consistently outperforming the segment-based segmentation as the postmortem interval increases. Our recognition model is based on a triplet loss training procedure. Using a ResNet 50 backbone to extract features from the regions resulting from our segmentation, we train our network to simultaneously minimize the distance between intra-class pairs, the genuine pairs, and maximize the distance between inter-class pairs, the imposter ones. In the end, our network is able to extract iris embeddings from the images. These embeddings can then be compared, and according to the distance between them, the network can make a decision whether they belong to the same subject or not. So how does this perform? So evaluation of our recognition method also shows that the postmortem interval affects the accuracy in recognition. While it is possible to achieve very high accuracy in pairs with shorter intervals, as we have here in the blue line that shows an area under the curve of 0.95 for pairs under 24 hours of postmortem interval. This accuracy decreases as the interval since the death grows, down to an area under the curve of around 0.78 for intervals longer than 14 days since death. And these are the results in our smaller test data set. In the newly collected data set with a larger number of images, we see a similar trend, but in this case, with much longer intervals. We have in this data set up to 69 days after death. Finally, we compare our method with the current state-of-the-art in postmortem iris recognition, showing that we have developed a competitive method. So to get to the main point, we combined multiple segmentation masks with the class activation maps produced by our network, and then we can compose a visualization to offer insights into the quality of the recognition decision. So in this case, over here, we have a genuine pair that resulted in a very good score, suggesting that it's a strong match. In the visualization, we can see that the wrinkled and highlight areas do not occlude too much the iris texture. However, the fact that the strongest network activations in both images are located outside the iris region can be used to argue against the output of the similarity score. As a counterexample, this imposter pair can also be disputed by considering the strongest network activations do not coincide with the iris area, suggesting that the quality of the decision in this case might not be adequate. And in this final pair, we can use the visualization to corroborate the strong similarity score that resulted this pair of images by verifying that there was a very good segmentation of the iris. There's low occlusions to the iris texture in these images. And most importantly, there's overlap in the strong activation areas of both of these images, confirming that this is really a good match. So to summarize the contributions of this work, we have collected the largest data set of postmortem images so far. Our mask RCNN segmentation has managed to advance the state of the art in postmortem iris segmentation. We have proposed a competitive end-to-end triplet-based method for iris recognition that is capable of providing human interpretable visualizations of the method's results, which can then give important insights to forensic examiners. And this is something that no method has done before for iris recognition. So thank you for your attention, and I will be available to take your questions.